Hi everyone, welcome back to Chem Story. Today we're diving into the IUPAC nomenclature of alkanes, how to systematically name different alkane molecules. Have you ever felt confused about naming organic compounds? Don't worry, we're going to break it all down step by step in the simplest way possible. We'll go through how to find the parent chain, number the carbon atoms, identify the substituents, and finally, how to put everything together into a proper IUPAC name. Alright, let's get started. Every alkane name has three main parts: the prefix, the parent, and the suffix. The prefix tells us about any substituents and where they're located. The parent refers to the longest continuous carbon chain, and the suffix shows that it's an alkane. So it always ends in -ane. Let's break that down with an example. 3-ethyl, 4-dimethylheptane. The prefix tells us there's an ethyl group on carbon 3 and 2 methyl groups on carbon 4. That's why we write 3-ethyl, 4,4-dimethyl. The parent is based on the longest chain, which has 7 carbons, so we use hept, and since it's an alkane, the suffix is -ane. Put it all together, and we get the full name, 3-ethyl, 4,4-dimethylheptane. Now that we've got the basics down, let's walk through the full naming process, step by step. Step 1. Find the longest continuous carbon chain. This chain decides the base name of the compound. If there's more than one chain with the same length, we go with the one that has the most substituents. That's what IUPAC rules tell us to do. The longest chain becomes the parent name, and any other carbon groups attached to it are treated as substituents. And since we're dealing with an alkane, we add -ane at the end to show that all the bonds are single. Let's try this with a real example. At first glance, the longest chain might seem obvious, but it's always worth checking all possible paths. In the incorrect example, only 7 carbon atoms were counted. But if we trace a different route, we can actually find an 8-carbon chain. That means the correct parent name should be octane, not heptane. Choosing the longest chain is the first and one of the most important steps in getting the IUPAC name right. So make sure to double-check your options before you lock in the parent chain. No matter how the structure is drawn, the first thing we always look for is the longest continuous carbon chain. In the image, the same molecule is shown in 3 different ways, but the longest chain stays exactly the same in all of them. Even if the drawings look different at first, the actual connectivity doesn't change. Here's a helpful trick. Start from a branching point and try tracing different paths through the molecule. Always choose the one with the most carbon atoms. If a molecule has 2 chains of equal length, here's the rule. Pick the one with more branches. Take a look at this example. Both options have a 7-carbon longest chain, but there's a key difference. One has just a single substituent, while the other has 2. Since the more branched chain gives us a more detailed and systematic name, that's the one we choose as the parent chain. In the second example, we're applying the exact same principle. Both options have a 7-carbon chain, but the difference is in the number of substituents. The correct structure has 4, while the other one only has 3. So once again, we go with the more branched chain. That's how we stay consistent with IUPAC rules. Now that we've found the longest chain, the next step is numbering the carbon atoms, and we need to do it the right way. Start numbering from the end that's closest to a substituent. That way, the first branch gets the lowest possible number, just like the IUPAC rules tell us to do. Let's compare 2 different ways to number this structure. In the incorrect example on the left, we start numbering from the leftmost carbon. That puts the first branch at a higher number than necessary, which means all the substituents end up with larger numbers. And according to IUPAC rules, that's not ideal, because we always want the lowest possible numbers. Now, in the correct example on the right, we start from the rightmost carbon. This way, the first substituent shows up at the lowest number possible. The result? A cleaner, more efficient name that follows the rules. Using this approach helps us come up with a consistent and universally recognized name for the molecule. Sometimes, branches are positioned the same distance from both ends of the parent chain. When that happens, we need a tiebreaker. If there's a tie, we look at the second branch point, and that's what helps us decide where to start numbering. The correct numbering comes from the end that reaches that second branch first. That way, we still assign the lowest possible numbers to the substituents, just like the IUPAC rules want us to. At first, both numbering options might look fine, especially since they give the same number to the first substituent. But we need to look a little deeper and check the second branch point too. In the incorrect example on the left, numbering starts from the leftmost carbon. The first substituent is numbered correctly, but the second one ends up with a higher number than necessary. That means the overall numbering isn't fully minimized, and the name ends up being less systematic. Now, in the correct example on the right, we start numbering from the rightmost carbon. This way, both the first and second branch points get the lowest possible numbers. The result? A cleaner and more standardized IUPAC name. By following these numbering rules, we make sure every molecule is named consistently with no confusion. Now that we've numbered the parent chain, it's time to figure out and name the substituents. In alkanes, substituents are usually alkyl groups, and these are formed when you remove a hydrogen atom from an alkane. To name an alkyl group, we just replace the ane ending of the parent alkane with -il. So if you take a hydrogen off propane, you get propyl. Remove one from butane, and you get butyl. But there's more to it. The position where that hydrogen is removed can change the type of alkyl group you end up with. Let's take a closer look. In propane, if we remove a primary hydrogen, that's a hydrogen attached to one of the end carbons, we get a straight chain group called propyl. But if we remove a secondary hydrogen, the one attached to the middle carbon, we end up with a branched group known as isopropyl. So even though they come from the same molecule, the type of hydrogen we remove makes a big difference in the structure of the substituent. The same principle applies to butane too. Where the hydrogen is removed tells us what kind of alkyl group we're dealing with. It's important to tell the difference between straight chain and branched alkyl groups, because that choice directly affects how we name more complex molecules later on. Getting these details right sets the foundation for clear and accurate IUPAC names. To make things easier, here's a quick table that sums up some of the most common substituents. You can use it as a handy reference whenever you're naming compounds. Now that we've got that part covered, let's move on to how we handle multiple substituents in a single molecule. After we've identified the alkyl groups, the next step is writing their names the right way. First, we write down the carbon number where the substituent is attached. Then we follow it with the name of the substituent itself. To keep everything clear and organized, we use hyphens to separate prefixes from numbers and commas to separate multiple numbers. For example, in 3-methylpentane, the methyl group is attached to carbon 3 in a pentane chain. Now, if a molecule has 2 or more identical substituents, we use numerical prefixes to show how many there are. Di means 2, tri means 3, tetra means 4, and so on. So in 2,3-dimethylbutane, we've got 2 methyl groups, one on carbon 2 and another on carbon 3. That's why we use the di prefix to show there are 2 of the same group. When multiple substituents are attached to the same carbon, we need to be clear about exactly where they are. Even if they're all on the same carbon, we don't just assume it's obvious. We list the number for each substituent. For example, in 2,2-dimethylpropane, both methyl groups are attached to carbon 2. So we write 2,2 to make their positions crystal clear. It might feel a bit repetitive, but it's important for accuracy, and it follows IUPAC rules. Now that we've identified and numbered all the substituents, the final step is putting everything together into one complete name. When a molecule has different substituents, we always list them in alphabetical order, no matter where they're located on the chain. It's not about position. It's about the name of the group itself. That's what determines the order in the final IUPAC name. Here's an important rule to keep in mind. Not all prefixes count when you're deciding alphabetical order. Prefixes like di, tri, tetra, sac, and tert are ignored when alphabetizing substituents. But prefixes like iso, neo, and cyclo do count when figuring out the order. It might sound a little tricky at first, but once you see it in action, it starts to make sense. So let's walk through a real example and see how this rule works. Following the steps we've learned, we start by identifying the substituents. In this molecule, there are 2 types, an ethyl group at carbon 3 and 3 methyl groups at carbons 2, 4, and 5. Next, we arrange them in the right order based on their first letters. We've got E for ethyl and M for methyl, and since E comes before M in the alphabet, ethyl goes first, followed by methyl. Even though tri tells us there are 3 methyl groups, We ignore it for alphabetical order. We only pay attention to the M. All right, now that we've got everything in order, let's put the final name together. The correct name for this compound is 3-ethyl 2,4,5-trimethylheptane, all written as a single word, with hyphens between numbers and words, and commas between multiple numbers. And that's a wrap on alkane nomenclature. I hope this lesson made naming alkanes a lot easier to follow step by step. Thanks for watching, and I'll see you in the next one.